In this second video, we will continue the discussion of field extensions that we started last time, which culminated in this theorem, where we prove some equivalent conditions of the algebraicity of an element A of an extension field E of the base field F over F. A being algebraic over F means, remember, that there's a non-zero polynomial with coefficients coming from F and with A as one of its roots. So that is equivalent to the ring extension of F by A inside E being a field, which in turn is equivalent to that ring extension having finite dimension as a vector space over F. So if any one of these equivalent conditions holds, then this degree is in fact equal to the degree of the this dimension is equal to the degree of the minimum polynomial of A over F, which is nothing but the unique monic polynomial that has A as its root. Now, remember that it is also the generator of the kernel of the evaluation map that takes each polynomial in Fx to its value at A, like this. So this maps the ring homomorphism into E, and its image is this, right? And since Fx, this polynomial ring, is a PID, its kernel, which is an ideal, the kernel of this homomorphism, which is an ideal, is generated by a single element, and that element can be chosen to be monic. Once you choose it to be monic, it's unique, right? There's only one monic such polynomial, as has A as its root, and it generates the whole ideal, the whole kernel. Okay, so that's what we did last time. Now we continue this discussion. Again, take a field extension. Here's some terminology. We call elements of E that are not algebraic over F transcendental elements. Namely, they're said to be transcendental over F. If all elements of a field extension are algebraic over the base field, we call that field extension an algebraic one. Right? So here's a word about notation too. Notice that Fa is not always equal, the extension of F by A as a subring, which is denoted by the brackets here, is not always a field, right? It's a field if and only if A is algebraic over F. So we still have a field extension inside E of F by A, which is denoted like this, and it happens to be the smallest field extension as such. So our theorem implies that the algebraicity of an element A over F is equivalent to this field extension being equal to the ring extension. Now, another thing that the theorem implies is this: if you have a finite degree field extension, which means the over field as a vector space over the base field has finite dimension. If that happens, then any element, for any element A of E, Fa, the degree of Fa as a vector space over F, or a dimension of it as a vector space over F, is finite. Therefore, by theorem again, Fa is a field, this extension is a field, and hence A is algebraic over F. In other words, finite degree extensions are algebraic extensions. What about the converse? Namely, is every algebraic extension necessarily of finite degree? The answer is no, as is illustrated by this well-known example, namely that of the so-called algebraic numbers. Algebraic numbers are the fields of complex numbers that are algebraic over the rational numbers. Okay? So once you observe that once you prove it's a field, it follows immediately that this A is the largest algebraic extension of the field of rational numbers inside the field of complex numbers. Okay? So we will prove it's a field, but we'll prove it for this more generic case where this is any extension and A is constructed similarly, namely defined to be the set of all algebraic elements of E over F. To prove it's a field means that A is a subgroup of E with respect to the addition of E, and non-zero elements of E, A, is a subgroup of the non-zero elements of E. That means we'll do this. But before that, we make an observation. First, start with this is useful. This will be useful in our proof of A being a field. So take a succession of two field extensions, each of finite degree. What does it mean? It means E is finite degree over F, and L is finite degree over E. That means we can find a basis of E as an F vector space, say AIs, a set of AIs, and the basis of L is an E vector space, say a set of BJs. So substituting here this form of E, we get this equality. Now, we would like each BJ jump over this direct sum, retaining the directness of the sum. Can we do that? Well, an easy fact to see is this: for each J, BJ multiplication by BJ inside E constitutes an F linear transformation between the vector spaces E and L over F. And it is evidently one-to-one because we are working in a field, right? L, that is. So being one-to-one, multiplication by BJ preserves directness of sums. That means BJ's jump over the direct sums. So we have this. And there are as many as m times n pairs of IJs, which yields this equality as desired. Okay, let's use it in the proof that A is a field. First of all, A is non-empty because 1 is in it. Okay, that was technically necessary. You take two elements of A, call A and B, and try to prove that A minus B and AB inverse when B is non-zero are also elements of A. Now you can appreciate the difficulty of doing this directly by using the definition of A, because you would have to find two polynomials with A minus B and AB inverse as their roots, which is a hard thing to do. But instead, we will follow a more devious but more effective route, and by using our observation. Now, A and B are two elements of A. That means they are algebraic over F, right? So then this extension has finite degree by our theorem, and this is a field, because A is algebraic over F. Also, B is algebraic over F, therefore it's algebraic over the larger field FA2, which implies that this extension is finite degree, and this is a field as well. Note that we denote the latter field like this. This is technically this is the smallest subring of F, subring of E containing F and A and B, right? But in this case, it's a field too. Okay, so now, so by our observation, since these are finite degree extensions, as we have pointed out while discussing the previous slide, so is this by our observation. What is the significance of this being a finite degree extension? First of all, both elements A minus B and AB inverse are there because they belong to this extension, because AB belongs to that, and it's a field. Therefore, these guys are there too. That means the extensions of f by a minus b and of f by a b inverse, they are both finite degree extensions because they sit inside this extension of f. I mean, as vector spaces over f, they are subspaces of this bigger vector space. So they have, each one has finite dimension. That makes these guys finite degree. These guys algebraic over f. Therefore, they belong to A. So this proves A is a field. But we are not done because there's an obvious question. Now we have F, a field, it's the largest algebraic extension of F inside E, which is A, and then there's E, and there may be elements in the difference. So one natural question is, if such an element as is in the difference of E and A can be algebraic over A or not. So can we extend A to an algebraic extension? In other words, the answer is no. Here's why. You take an element B of E, which is assumed to be algebraic over A. That means there's a non-zero polynomial f with coefficients coming from A, and with B as its root. Okay? Now, let C be the set of all coefficients of f in A. Note that it's a finite set of elements, each of which is algebraic over f by definition. And since this extension of f can be obtained successively as single extensions of f by each element of C, one by one. Once you exhaust C, you still have a field that has finite degree over the base field f. It's easy to see that, right? So this extension has finite degree, and obviously B is algebraic over this field. Therefore, this extension has finite degree too. So according to our observation, that simple observation that we proved, then the extension of f to fb is algebraic too, because it sits inside this. So that puts B in A, proving our corollary. So this concludes the second part of our discussion. Thanks for listening, and hope to see you next time.